I'm MC Toon, the worst rapper in the world. How are you doing tonight? Tonight we have an unconventional flat earther, as I said, as I put it in the description. We've got Zechariah Edwards. Now, he is unconventional in that I don't know if you're going to hear a lot of the same things as we hear from other flat earthers. So, how you doing there, Zechariah?
I'm great. Thank you for having me.
Is it Zechariah? I don't want to get it wrong.
First time, Zechariah. I like that.
All right, good.
You're the first person who called me by my right name.
Well, maybe your parents got it before I did. So, well, yeah. Glad to have you here.
So it's kind of like that. I've nailed on chalkboard that.
So, all right, your audio did clip out a little bit there, so it might be trying to cut out a little too much background. I don't know if you can edit that. He was working on a little bit of a background noise suppression thing for a bit.
Let me try this. Medium. All right, let's try that.
Okay.
Maybe I raised my voice too much.
Yeah, the people are saying that the black screen is or blue screen is a little choppy. So this is the built-into Zoom green screen effect in it, and if you don't have a green screen, it'll still do it, but it's not quite as good. So that's what you got. Now this is my first time in 1080, so you'll be able to count my eyebrow hairs or lack of them, I guess. So Zechariah, why don't you tell us a little bit about yourself, just in general, and then we'll get into how you came to think the world was flat.
Okay. Yeah, I grew up like everybody else, just interested in science and, mechanics and globe orbits. I even got interested in Albert Einstein and his theories of relativity. But I didn't have much of a good education. So, I wasn't indoctrinated in any way. I just it was an interest. I looked into it myself. And I find that I'm able to look at it from a more objective perspective and not be so dogmatic about my belief systems. Other than that, I just try to raise my family, and we're here in Tennessee right now, enjoying the weather and enjoying trying to get my wife's AT license. She'll be an aircraft mechanic pretty soon. Hopefully by tomorrow. We'll see. She's going to go get her license.
Wow. Somebody's asking when I'm going to grow a mohawk. I have rocked a mohawk. So,
you put some gel in your hair. Huh?
That's just, yeah, it's the faux hawk right now. That's
right.
What I normally do. So, so how is it that you came to think that the Earth is flat?
Okay, so I'm really not on borderline. I don't know if the Earth is flat. I don't know if the Earth is a globe. I'm borderline, where I can look at both sides. And this started about 4 years ago, I would say. By now, what was it? I watched this video on YouTube. It was called "They're Hiding God with the Biggest Lie Ever," I believe is what it was called. It's not the new version that's out. It was an older version, and it seemed more like it got deleted or it got censored, or I don't know what happened to it. I can't find it anywhere on YouTube anymore. But man, I started looking into it, and I was like, I don't know, maybe we have to look at it from all sides of the spectrum. So I decided to. Here we are today, still looking at it, but I'm leaning more towards flat, and it could be a globe. I'm not dogmatic about it.
All right. Do you think that the Bible somehow informs you?
I have looked at a lot of scriptures, and I believe in evolution. I believe in some of the things that science says regarding evolution, and I'm not completely dogmatic about, 6,000 years, all the all the wording, it's more metaphorical, it's more poetic, you know. So when it says the circle of the earth, you know, it's poetic, it's metaphorical. I don't know if it's a globe or, you know.
All right,
or a flat circle.
So it's definitely unconventional. So
yeah.
So all right, some people are talking about pineapple pizza. I made pizza today, right there, some pineapple pizza.
Nice.
With chopsticks.
Wait, can you show me the pizza? Is it flat?
Yeah, but this pizza is rectangular.
Oh.
So, okay. So it's not like, you know, because there's plenty of flat earthers that are like, well, the Bible says it's flat, therefore it's flat, and ignore everything else, right? That's not right. You. You are, the evidence makes you think that it's flat, right?
Right.
Okay.
Yeah, I'm looking at the evidence, exactly.
So what was the evidence that, like, was the thing that, like, really nailed it for you?
So I was looking at Newtonian physics, and what we have in Newtonian physics is the three-body problem. Okay, you got the Earth, the Moon, and the Sun, and the Moon is in between the Earth and the Sun, you know, on orbit. Well, the Moon should get pulled away by the Sun. This is the three-body problem that is not solved yet. Why is the Moon not orbiting the Sun? Why is it orbiting the Earth? You know, if Newtonian physics was a valid theory.
Well, yeah, I think the three-body problem is not a problem in the physical world. It's more of a problem in our ability to model it. Right.
Right.
So, if it happens, it happens, and if it doesn't, it doesn't, and we just can't correctly model it, right? So what we do when we model the Earth and Moon and Sun, we treat the Earth and Moon orbiting the Sun as one body with the barycenter, which is slightly off center from the Earth's center. Right, halfway, right. You know, partway towards the Moon, still within the Earth. The point is still within the Earth, and that's what orbits the Sun. So that's how we calculate the orbit of the Earth when we need to be precise.
And so that's the kind of stuff I'm still looking at, as far as like mathematically. I got to see it for myself, and it takes a lot to learn all this stuff. They don't teach you this stuff in school, you know.
Well, it depends on your school. So, like I took in Minnesota physics in this the science in your senior year of school is not required. I took it though. I took the optional physics class and did well, loved it. And when I went to university, studied all sorts of different physics and chemistry and math that covers all this stuff. So, you know, it depends on your schooling, right?
Yeah. So my level of education is just enough to be an aircraft mechanic.
Okay, so you can't maybe say we didn't learn that in school, because some people do, some don't.
Right. Yeah.
Right. Okay, so the three-body problem was it? That's definitely not something I've ever heard anybody else say was the thing that got them. Normally they kind of go into a bunch of things that aren't really supported by evidence in any way. That's just basically contradicts reality. So you know that the curve of the Earth, the radius of the Earth, has been measured, right?
Okay, so taking two sticks, right, and measuring the degree angle of the Sun or something.
That's the 2,500 year ago version. We've done much better than since then.
Okay, so how do we do it today?
We do it today with satellites.
Okay.
But let's back up and not do satellites, because a lot of flat earthers are like, well, there's no such thing as satellites. It's all just lights in the sky. So there's ways.
Not one of those flat earthers,
I know. We can get into that later, because that's some of the crazy. I gotta say, it's a little crazy. I love it. It's funny, kind of fun, but without using satellites while staying on the ground, surveyors have done it. And the most rigorous ones that they did were of measuring the radius was they started at one point, like on the United States, on the East Coast, and they very, very accurately determined their latitude and longitude using celestial measurement techniques, right, to get their position. Then they measured the length along the 39th parallel all the way across the United States to the opposite side on the West Coast. And same thing, they took days and days and days to accurately get the pinpoint precision of the location of that point. And then all of the surveying techniques that they used, none of them are sticks and shadows, to measure that length across there. While they were doing that, the way that surveyors do it is the fundamental thing is triangulation, right? So if you know this is you probably covered this well enough in school, but a lot of people don't do it often enough to remember it. But if you know 3 facts about a triangle of the 6 facts that there are, in all but one case, you can solve the triangle, which means you can get the other parts of a triangle, right?
Right.
Have you heard that, right? So if you know 3 sides.
Yes.
You
yeah.
can- you
A
can-
squared plus B squared equals C squared.
That's only that. Yeah, that's for a right triangle,
Okay.
right? So if it's just a generic triangle, you use the law of sines for any triangle. So if you know 3 sides, they call it side, side, side. You can calculate the angles. If you know one side and an angle and another side, then you know side, angle, side. Is this starting to ring a bell a little, maybe?
So that picture right behind you there, you're saying that triangle.
Right
they
here?
Measured that. Yeah.
No, this wasn't surveying. This is a flight route.
Oh, okay.
That's what this was. Yeah.
I was trying to think of that triangle. You know how you make 3 right angles and you end up.
Yeah, that's what that is. So we'll get to that in a second, because that's kind of right in the same line.
So that's not measuring the radius of Earth, though.
This was not.
Oh, yeah.
No.
Okay.
That was a challenge that somebody issued. He said $100,000 if you can do a triangle with 3 90-degree angles in it, and he was going to pay $100,000, and I did it. So he owes me $100,000. So there's that. Got that going for me, which is nice. So so triangulation. This is important. This is I don't want to get off on track on that. So I'll draw a triangle here. It doesn't matter what we have. Any triangle, as long as you know the right information, you can solve it. Right? So that's not a right triangle. You can't use a squared, b squared, c squared. But if you know side, angle, side, you can solve for the rest of it. If you know angle, angle, side, you can solve the rest of it. If you know angle, side, side, that's the one you can't do. You need one more piece of information to do angle, side, side. So if you're surveying, what they do is they'll start with a known length. Right there. They'll know this. And what they do is they back in the day, they used chains. Long chains, very long chains, and they were extremely precise about it, and they were particular about the the temperature, and they included the temperature in their measurements so that they could adjust for thermal expansion and contraction. Right. So they'd start with that length there, and then they go over here on this other side. They'd measure that angle. Right. And then they'll get another length, right? But they typically start with one. They'll do 2 angles, right? I think that's kind of how they start. They got angle, angle, side, and then you can solve the triangle. And once you start with that, then they make an entire grid of triangles all over. So I'll draw a couple more here.
You're pretty good at drawing triangles.
Well, I'm cheating. I have a ruler. And once they do that, right? So here's just at the beginning of one. And there's when they do this, so they document all of it. So all these triangles are documented, the sides are all documented, the locations are documented. And they don't just make one measurement. They'll make many, many measurements over the course of many days. So when you get lots and lots of measurements together, then you can do some statistical analysis to see if you have a tight standard deviation and if your margin of error is within a certain acceptable range. And if it's not, start over, right? Or find out the errors and fix them. So
wouldn't that work on a flat Earth circle at the same time?
It would work on a flat Earth or a spherical Earth, absolutely. But what doesn't work on a flat Earth is the number of degrees in the triangle. But I'll get to that in a second. So they do this, they make this grid all the way across the entire country of the United States. And then they know the length to an extremely high precision of that particular distance. And it was right along the 39th parallel. Now, they also used a measurement that started in Canada, went all the way down to Mexico, of a similar nature, just going straight north and south. Doing that, they're able then to calculate, it's actually a measurement, measure the radius of the Earth equatorially and in polar, the polar radius. And they get actually a different polar radius and equatorial radius. Now, here's the cool thing. That's not the only time it's been done. It's been done in India, it's been done in England, it's been done in Europe. It's been done by different people at different times using different and similar techniques. And they all, without talking to each other, without even having the same people on the team, because they're done enough years apart that they're not even living, they get a number extremely close to the others, right? And there's always a margin of error. So that's the awesome part about that is that the agreement in the numbers gives us super high confidence that it's correct. All right, so go ahead.
Oh, okay. So the South Pole, how did those chains survive the South Pole? Or how were they even able to drag them across the ice?
They didn't measure the South Pole. They measured several different places, but the South Pole wasn't one of these surveys that they did.
Okay, so they did it like at what is that called? If you lay a ribbon along the globe, right, it will form like a angle around it.
Yeah, an arc around it. Yep.
Well, it won't form a straight arc because if you lay it flat, it will have to form a curved angle, right?
Yeah, there's no such thing as a straight arc, of course.
Right. Well, yeah, because like that ribbon is flat, so you'll have to I'll have to bring up a picture of it to show you. But I see that globe right there behind me, and so you're thinking they did that like from India to Australia, from.
So yeah, Sir Everest did it. He actually it was a long. The one in India was longer than Everest was able to complete. It completed. I think he published like his initial, but the full survey of India was done after he died. Was completed after he died. The French did it. Oh yeah, the French did it during the French Revolution. Of course, probably mostly in France. I don't know. Maybe it was elsewhere too. I don't know about that one. So yeah, America, India, England. So Airy, Airy's failure, if you've heard that, Airy did it in England, same place, but of course it's shorter. He couldn't do as much distance as in America, so the accuracy or the margin of error is a little bigger. They've done it in South America, so I don't know. Like I said, the initial measurement was when they used the chain, and they'll do it at different points along the way to verify everything and check their numbers. But for the most part, it's triangulation. So they're not doing chains for all of it. So all right. But here's the cool thing: if it's flat, every single triangle sums to what? How many degrees on the internal angles of a triangle?
What do you mean by internal angle? 90 degrees?
It's 180.
180.
Yeah,
Oh.
every triangle on a flat surface sums to 180 degrees.
Oh, I see what you're saying.
Right.
Yeah.
So that's not a trick question. That's just, that's middle school geometry, right? But on the surface of a sphere, every triangle is more than 180 degrees.
Right.
Now, that's not typically covered in high school, I think. My sister recently was taking a high school math class, and I was her math tutor. And that was one of the things that we covered, was that little bit of spherical trigonometry to look at what triangles on a surface of a sphere that are more than 180 degrees. So that amount more than 180 degrees is called the spherical excess.
Right, yeah.
So go ahead then.
My question would be, well, I don't believe the Earth is completely flat, but would that work on a curved, dome, more or less?
Would it work like if the Earth was a dome?
Like a dome, or you've seen the picture of the old Ferguson Earth, right?
That looks it looks like a donut was sat on it and then lifted up, right? So
right.
Like you got the North Pole in the middle, and then it curves down, and the equator's low, and then it comes back up towards.
Right. Yeah.
Yeah. Well, that's
what do you think?
That's pretty silly, because if we're in North America, we could see South America. If that was the case.
Yeah, that's true, unless the atmospheric conditions, because you're seeing through three atmospheres.
Hold on though. We can see the stars immediately. Hold on. Immediately above the horizon, we see the stars. Right. So if we're on the downside of that in North America, which according to that map we're kind of slanting down towards the equator, we would look slightly up and see South America out there. But we don't. We see at night, we see a horizon and we see stars, right? So we can't be the atmosphere might not let you see the land, because we can see the stars and we don't see the blacked out area that is where the land would be if we can't see that far.
All we really see that far is okay, they did a scientific calculation how far the eye can see.
You're gonna need a citation for this one.
Okay, the way they did it, I'll look it up. They used a candle, and they said, okay, this is equal to, what is it?
That's just for a certain amount of brightness. But if something's really bright, that's not what they're measuring, because if it's really bright, you can see it no matter how far away.
They said that the candle was equal in brightness to a star, right?
At some distance.
Yeah. And then they determined, okay, with this brightness of a candle, we can't see further than, what was it? I think 1.26 miles or something. Let me look it up.
Yeah, but that's one candle. We're talking about being able to see an entire continent with the sun shining on it. That's a lot brighter than a candle. Plus, you can see all the stars.
Yeah. Let's see here.
Plus, you got
1.6 miles with that candle, detecting a candle flame.
Yeah. So, plus you got some explaining to do for why we don't just roll down and collect down in the equator there.
So, do you know about space-time curvature, acceleration?
Yeah. We just generally call it gravity.
Right. Yeah. So, if the Earth were flat, it would still work. Gravity would still work. And I'm not one of those flat earthers who say gravity doesn't exist and all that.
So, all right. So, can we put aside that idea of that particular the kind of, I don't know.
Okay, yeah, we'll just go back to the flat. But that I'm not one of those flat earthers who say there's no curvature, and I just wanted to make that clear. There is some curvature.
If there's some curvature, that means it's a sphere.
Well, you don't think a dome has curvature?
Oh, like we're sitting on top of a dome?
Yeah, like you're sitting on a dome.
Okay. So yeah. Okay, let me think about that for a second. That's so a dome earther then. That's new. Um,
Yeah, so right, it's halfway in between. We're meeting in the middle here.
uh, the geometry isn't a compromise, by the way. Um, okay, so if we're on a dome, the
Okay.
curvature rate of that dome is uh, is measurable, right? We can measure it through different
And
different methods. We could, right?
that's why the past few weeks I've been just focused on trying to see what the rate of curvature is, or
Yeah.
amount of curvature.
So yeah, I've seen you working on some of that. So let me see here. So there. Oh, I need to get a thing. So there are consequences of the Earth being about 4,000 miles in radius, right?
Right.
The amount of curve in a certain distance is a certain amount. So Extra J says, you did say unconventional. Yes, unconventional is true here. So okay, so I gotta bring up something here. Little edit quick on here. There it is. So yeah, so the amount, the curvature amount, matters. So let me see if I have. There we go. So my favorite curve calculator, whoever was doing it, abandoned the site and it's gone. So
Oh no.
so yeah, so so Walter Bislin has a fantastic one. There's nothing wrong with it. It's a little complex. Is about the only issue, and I like to just have enter these things and that's it, and then give me several options. This lets you choose the amount of refraction, and refraction is never zero, but it defaults to zero. So, that's not. And what's a reasonable amount? What's common? It doesn't say, right? So, but the nice thing about it, and so I should share this to you, I suppose. Do you want to see this?
Sure. Yeah. Please.
I will. I'll send everybody the link in the chat there. I'll send it to you in Zoom, and then I'll share to you the thing. You're on a desktop, right?
Right.
Okay, so you can. There you go. I sent it in the Zoom meeting. You should be able to just click on it.
Okay.
So actually, if you just pull that up, you can kind of follow along. And so if you want, what we can do, and this is typically flat earthers don't want to test their claims. They like to use this 8 inches per mile squared, which is the wrong formula. And the formula is not wrong because it's a parabola. It is a parabola, but that's not the reason why it's wrong. The reason why it's wrong is because it doesn't have a way to include the observer height. And every observation has an observer height, unless your eyeball or camera is half submerged by water in the ocean, which I've never seen anybody present that picture where the bottom half is in the ocean, right? Because you really can't.
I've seen something pretty close where, like, the field, like on a football field, you have it down at eye level, and you see the guy like disappearing over the horizon on a football field.
Yeah, but a football field is intentionally curved to shed water.
Okay.
So that's a bad example. They like to do it over water, and of course when you're when you're really close to water, there's a large amount of refraction, and it's an extremely variable amount of refraction. So you don't even know how much to put in there to when you're doing your calculations. So it's like it's a self-fulfilling prophecy, and they're kind of intentionally doing it, and then also intentionally ignoring the conflating variables, like the extreme amount of refraction. So an observation from a high elevation away from that refraction is a great way to do things. So if you can be 100 feet above water, that's great. You see farther too. So the curve calculator is good, but here's the cool thing about the curve calculator from Walter Bislin is he derives all of these formulas. So right here, if we go down to exact equations for the hidden height. Ooh, I double clicked on it, like letting it log in to edit the thing, right? So he gives these formulas here. He doesn't just give the formulas, he derives them. So that's what all this is here. The exact distance to the horizon, and there's two different equations. The reason why is because there's two different ways you can get that distance, and then he has an approximation here. So this the reason, so the two different distances, or two different ways to do the distance. One is the line of sight distance between observer and target, tangential to the surface of the globe, which typically we don't know unless you did a laser distance measurement. And then
is that the same thing as parallel to the surface, or parallel, eye level, parallel, tangent?
No. No, because parallel to a curved surface is a curved surface. Tangential to a curved surface is a plane. Or in 2 dimensions, it's a flat line.
Okay, so we're saying the eye level is a plane, right?
Yes, when you're looking at something, eye level is a plane, and it's perpendicular to the downward direction.
Right.
So I can draw that. And I don't have a cheat for drawing a curve. Well, I do. I don't know. I usually have a little echo sitting here, but all right, I don't. So here's the curved surface. Right there. I'll go. Gotta switch this here. And then we've got tangent to that. So down is this direction here, and tangent is this. There you go. Right?
Right. Okay. Okay, so that curved line is the radius?
The curved line would be the surface.
Or the
yeah, the radius would be, it'd go farther down because this circle's too big to fit on this paper.
Okay.
Right. So that would be in 3 dimensions. This line here would be a plane going this way too. It's perpendicular or orthogonal to the downward direction. And so if your eyeball is half submerged, that's this here. But if your eyeball's not half submerged, right, eye level is then this, right, this higher amount here. So when you're at high elevation, when you look when you're looking down to the surface of the earth, there's a dip, right? There must be a dip to the horizon, right?
Right.
This angle here is the dip, and that can be calculated too. That's
1/69th of a degree per mile, right?
No, the dip is based on the observer height and the radius of the Earth, and I don't know if he includes that in here. That doesn't have the dip in here, but I do have the formula for that. It's not that complex. Let's see. We call it the drop. I did a video on it actually. Angular drop. No. And the cool thing is at about 35,000 feet, it's 3.2 degrees, which isn't that much, actually. And we don't... our eyes aren't really good at measuring angles. So if you're looking out an airplane window and you look at the horizon and you don't have any reference to where eye level is, you don't know that the horizon is different from eye level. It's just not far enough away from it if it's just 3 degrees.
Yeah, it's really hard to tell that.
Yeah.
That's why flat earthers say the horizon always rises to eye level.
They do, and they say that because they've never measured it. So, all right, so I'm giving up on looking up the formula. I can give it to you later if you want, or people can Google it. To continue the flow of the conversation. Rather than that, what I'll do is I'll pull up a picture that I took when I was flying back from Alaska last year in a plane. It was in the middle of the night, and the moon was out, and I got my theodolite app on my phone, which I had just the day before calibrated at the mouth of the Kenai River near Anchorage. Now, you were in Alaska for a while, weren't you?
Yes, I was. That was beautiful.
Did you?
Actually, I went to the Kenai River.
Yeah?
Yep.
So I was there during salmon frenzy, they call it, and people will stand out there with these dip nets, and the salmon will just swim right in. Right. And hundreds of people just there. It was crazy.
How long ago was that?
That was last July.
Last July. Okay, so we were there in June.
Did you leave in June?
We left in June, right before the salmon run. I was so pissed because I didn't get to go fishing.
Well,
right before salmon season.
Yeah, it's my understanding that like people that live there, they get to go for free or for some nominal fee. But if you're not, then you pay a good amount. But all right.
Yeah, it was $5 for me. The fee.
Oh, that's not bad. All right, so I'm going to share this to you so you can see it. Where'd it go? Got to find this. Everybody at home is looking at it right now.
You're sharing their screen to them. So
yeah, they see it because I'm doing it in OBS. All right, so now you see this picture I took in the theodolite app. Right? So that bar across the middle there, horizontal bar, is true level.
Yep, 0. Okay.
Yeah, and you see plus 0.1 degrees. There's actually 2 bars in there. One is at true level and one is slightly above, 1/10 of a degree above. The bottom bar is true level. And you can see the top of the moon is even with true level. Which, of course, is not possible if the Earth is flat. Right?
Why is that?
If the Earth is flat, then not a dome, right? If it's flat, then no matter how far away you are from the horizon, or from the somewhere on Earth, unless there's an edge and there's people falling off of it, right? Which generally flat earthers don't say is the case. The angular size between the far distance that you can see, 40,000 miles away, or 40,000 kilometers away or more, the angular size is so small that it will be at high level. It has to be at high level. This is the geometry of it. When you take into account refraction in the atmosphere, because of the layers of density, will actually make something rise up slightly. So everything on a flat Earth would the horizon would be slightly above eye level, right? But the moon here is below eye level. So if the Earth is flat, then the moon would have to be like inside the Earth somehow, and then the rest of the Earth around it has to be missing or something. I don't know how you do that. It doesn't make any sense. Also, if the moon is doing circles around above the Earth, some
right, yep,
thousands of miles above, it could never appear that low because of geometry again, right? We can do some triangulation to figure out, based on how far away the moon is, how high the moon is, what angle the moon must be above the horizon. It could never be below true level, no matter how far away it is. It's always above true level if the moon is actually above. What's that?
Unless the Ferguson model is correct.
The Ferguson model would have to, yes, but here's a problem. I'm going to stop to share. The problem with the Ferguson model is that it introduces a whole bunch more problems. That then you're trying to solve one,
right?
And it introduces a ton more, right? So you went from 99 problems, and you tried to solve one. You're not at 98. You're at 163, right?
Yeah.
So
that's where we got to weigh the balances. And I'm all about the science and looking at both sides of it and trying to debate it. You know?
All right. So let me do this then. That wasn't a quantification, right? There's no measurements there. That's just, is it above eye level or not? Yes or no. It's a qualitative observations, but we can do quantitative measurements of, and I'm going to share this to you again. So this is on my website, mctoon.net. This is the horizon does not rise to eye level. So let me share this to you. There you go. All right, so now you're seeing this. Now, I'll roll through these here. I'll say first that Robotham, who kind of is the grandfather of the modern flat Earth movement in the late 1800s in the south of England, claimed that the horizon always rises to eye level, knowing full well that his audience could not actually measure it because there were theodolites, but nobody had them or ways to measure it. But when the surveyor said, "Hey, we can measure that the horizon does not rise to eye level," he said, "Oh, well, there's collimation." But there's solutions to collimation. Collimation errors is when you look through the telescope of the theodolite, and there's the crosshairs on it to measure your up and down angle, right? Mm-hmm. It can be slightly out of kilter and cause you to read high or low, right? So
right, yep.
so now notice the black end of this is pointing towards you. So what they do is they turn it this way, and then they turn it this way, right? Now what they've done is they've inverted it. It's now up is down and down is up. So any errors that were measuring up before now measure down, right? Oh, people are wondering about the Ferguson model. We'll get to that in a second. So now any errors are now the opposite direction. So what you do is you just average your two measurements together, and it nullifies the collimation errors.
Right.
Okay. You don't just do two measurements. You do a bunch. You do 4 or 6 or 10. So
is there a way to use a plumb line to measure level and for a camera? That way you're actually measuring level.
Well, yeah, that's exactly what a theodolite does.
Okay.
It uses you drop a plumb line above you drop a plumb line so that you know where you are. So a lot of the time they'll put it above a plate that's embedded in concrete, so that it doesn't move, and then they'll center it right on the dot there. But they actually have then little screws that you adjust so that you can get it level, or the more advanced ones will do it automatically. It'll just automatically have little motors in it to level it, right? So all right, let me get this. So a guy called the Maine Surveyor did this. Now, he's a licensed surveyor in the state of Maine. He did this observation at Williams Reset, which is just the name of a place. I've got the coordinates there. And the elevation, 21.986 meters, right? And here's what he did. He looked through the theodolite there, and you're seeing this, right? It did not rise to eye level.
Right.
Right.
Yeah.
And you see at the top there, it says 90. So that's where the camera was like this, right? And then the 270, he flips it, and now it's the opposite face. And so instead of being 0 degrees is up and 90 is this way, now it's 0 degrees is down and 270 degrees is all the way around the other direction, right? So that's how they do their job every day, is they do this flip.
Okay, for me, so I would want this done like from the South Pole, from Africa, from a lot of different points in the Earth.
Sure.
That's it.
Yeah. So and I can get you one here in a second. So anyway, so here he's tipped it down so he can measure the angle down from true level down to where the horizon is. Then there's this logbook this is just the surveyor's logbook. He did 20 different measurements, 10 pairs. So you see 90 and then 269, 90, 269, 90, 269. And he averaged them all. So a total of 20 measurements, alternating so that he can negate error due to collimation. And he gets his final number of, I always miss where that is, 7 arc minutes, 39 arc seconds. So an arc minute is 1/60th of a degree. And an arc second is 1/3600th of a degree. Right?
1 mile is 69 degrees, or 1 degree, right? Or 69 degrees is 1
No.
degree.
This is just a way to measure angles. This isn't at this point anything doing with distances.
Okay.
Right. So he measured. So here's the deal. He measured the angle, the dip of the horizon, and then if the Earth is a sphere of radius about 4,000 degrees, then there's a certain dip that it predicts, and there's a certain amount of refraction that we know happens. The U.S. Geological Society uses 4/3 R. It's actually a K value of 0.33. And when you use that particular value, you see this refraction corrections 24,102. That is very close to the accepted radius, I think circumference of the Earth, 24,000 miles.
Right.
So he used that. Now, all right. So you said you want to see elsewhere, right? So this is in Maine, right on my website. Same thing. Let's see where to go. I have a bunch of pictures here from airplanes. There you go. All of them have the coordinates in it. Don't think I have it linked off of this page. Okay. So I might have to. I have one from New Zealand as well. Ah, darn it. I'll have to search it up on my own WordPress site. I don't know. I should link that in there. I have a lot of things on there that I want to do on my website and a lot of data, so sometimes I forget some things. So yeah, some guy in New Zealand did the same thing. He did a lot more, actually. There it is. He did many more measurements, and he used geological survey markers so he knows where he was and he knows the correct elevation. Let's see if that works. If we just do this. Search. There it is. All right. So this is a guy, Robin Bodley, and he went around. He took a picture of each spot that he took the measurement from. So here's 1, 2, 3, right? All these different ones. And they're all over these geological survey markers. There you go. And he didn't do 20 measurements each time. He did 4 each time. So let's see. And then here's then he graphed them. And so you see this, the top arc is the non-refracted dip based on the height. And the bottom arc is the refracted dip using, I think he used, I don't remember if he used 0.17 or 0.33 for the refraction constant there. So anyway, our coefficient of refraction. But you can see the X's, those are the actual measurements that he did, and it matches that bottom curve very nicely. So that confirms, again, from New Zealand. So we got Maine and New Zealand confirming the radius of the Earth through precise measurements.
This graph looks like a parabola, huh?
Parabola, it is, yes.
Yeah.
Yes.
So is that saying the Earth is a parabola?
No. The formula for the dip of the horizon with increasing elevation is a polynomial with a second order polynomial. So it's a x squared formula. So yes, it is a parabola. So there you go. Let's see. I got a couple comments here. Some people have said, let me do it while you think about that. So Baron Von G says for $4.99. Well, he didn't say anything. He just did a super chat for that. Thank you very much, Baron Von G. Bella Charge for $5 New Zealand dollars. So New Zealand right there for the win. He says he knows that when something gets so large and has the gravitational pull of the Earth, it will pull it into a ball / half Earth or hashtag half Earth. So we'll get into that in a minute here. So, all right. Any thoughts on that, Zechariah?
I'm trying to understand this graph. This is a linear measure from the dip angle in degrees, right?
Yes.
Okay, so he's saying for every point of a degree, height above sea level in meters. He's looking at, what is that, height above sea level in meters? What does that mean?
Height above sea level in meters is height above sea level in meters. I don't know how else to say that.
Oh, I see what he's saying. So this is, he went from 0 to 100 up, right, straight up, and started measuring different elevations, right?
Yes, yep. So he actually did... Excuse me. He did a lot of work. He pre-selected all these geological markers based on elevation.
Okay.
And most countries, many countries, I don't know if most, but many countries, the United States, New Zealand, obviously, publicly publish a lot of their surveying marker data. So there's actually a website you can get on your phone. And I was recently in South Dakota, and couple times I pulled out my phone to see if I could find any nearby geological markers, but there were just like, we were doing stuff. My wife's like, right. Why you gotta do this stuff? Get off your phone. I'm like, all right. We didn't have good coverage anyway.
Mount Rushmore, or what was that?
What's that?
I saw that mountain with the face.
Yeah, we went to Crazy Horse.
Crazy Horse.
Crazy Horse is Crazy is a great name for it. It is insanely large. It's so cool how big it is.
Oh, wow.
One of the things I like about it, about Crazy Horse, is the guy that started it knew that it would be more than his lifetime to do it. That's how big his dream was. And so he laid out all the plans to do it, knowing that it would be after he died. And they have continued after he died in the 80s. And his wife continued until she died in 2011, maybe. And now his kids and grandkids are working on it, and other people. So, yeah. And the guy, what's his name? Zilkowski is his last name. He actually worked on Mount Rushmore too. So he had some experience on mountains.
Right. That's pretty cool.
So, all right. So where are we? All right. So let's get out of here. So the thing is, let's see. The thing is that there are ramifications, consequences of a hypothesis. You know,
right.
The hypothesis being the Earth is this big, and so those confirm them, both in Maine and in New Zealand. So the Ferguson model. So let's Ferguson Earth. Let's see if not news. I need images. I think it's. I mean, it's. Ooh. All right, here we go. This is a pretty nice one. We can zoom in. All right, so here it is. I'm showing them at home. You've seen it. I'll just show them at home. So
Yeah.
here's the Ferguson idea. The North Pole is a high point, and then it curves down to the equator being kind of the lowest. Maybe the Tropic of Capricorn is the lowest. I don't know. And then it curves back up to this actual like uphill to get to Antarctica. And then he has like these bars that are holding up the sun and moon, right? Or things, I don't know. But there's, like I said, if you were in, if you were in Newfoundland there, over in Canada there on the East Coast, and you look straight south, you'd see South America. You'd see Cretan Bull. Thank you, Cretan Bull. Korchik Zulchek. Korchik Zulkowski was the guy's name that made Crazy Horse.
Oh, nice.
So,
okay.
All right. So yeah, you'd see South America. Everywhere else, like middle of where I'm at in Minnesota, we'd look due south, and we'd see the Pacific Ocean there, the South Pacific Ocean, just up above the local horizon. There'd be a secondary horizon or something. I don't know. We would see it, and then we'd look up even farther, and we'd see the edge of Antarctica, and then above that, and only above that, would we ever see the stars.
Some places on Earth you see so far, like over Lake Michigan, you could see the skyline of Chicago from Canada or something. And
well, not from Michigan, right?
From Michigan, yeah.
But that is you never see the bottom of those buildings. So let's not talk. We'll come back around to that if you want. Yeah, but this is the Ferguson model. So what about the Ferguson model? What makes? I mean, because you can't see. It's easily disproved because you can't see what you must be able to see.
Yeah, but the question is, should you must be able to see it because of the atmosphere? You have 3 atmospheres or 4 atmospheres, however many you're looking straight up. You're only looking through one atmosphere of horizon or to the stars. But looking at the horizon itself, it's converging. Everything's converging into converging lines, into the horizon. So it's like you're not really being able to see that far to see Africa from.
But why can we see the stars immediately above the horizon?
I'm thinking you're looking, when we look up at the stars, we're looking at the future, where if you're thinking of flat space-time, right, and Earth is, or you could say we're looking at the past, because when I look at the sun, I'm looking 8 minutes into the past, right?
That's if you accept that it's 93 million miles away. Yes.
Right. So, and then if I look even further,
5. Yeah.
Yeah. If I look even further, I'm looking into like billions of years into the past, right? At the stars. Do you accept that premise?
Of course, yes.
Okay. So that would mean that everything above me is in the past, and I'm the present, and I'm headed toward a future, which is a black hole. That's the future.
All right, but here's the problem. That doesn't answer, because the Earth isn't that big, right? From the North Pole to the South Pole, there's only a certain distance, and that distance, the measured distance, is 20,000 kilometers. So even on the Ferguson model, it's in the range of 20,000 kilometers. No matter what, you can't really get away from that, because like you mentioned earlier, there's 1 degree latitude is 60 nautical miles, which is about 69 miles, which is about 110 kilometers, right? So you add that all up, you get about 20,000 kilometers from North to South Pole. So to that ring. So if you're if you're really far north, it's only 20,000 kilometers. So, but you're seeing the stars immediately above the horizon. You don't see that ice ring that you would have to see. Why would you not see what's there?
Because you're up on that North Pole dome,
No, I don't know. You're
looking right over the edge of the ice wall, basically.
Yeah, but you have an excellent perspective to look at it and see it, right? But not even the North Pole. You're in North America, right? We're on the downsloping part of it. So up for us is this way.
Right.
Right. I think this deserves another piece of paper.
No, I know what you're drawing.
But I'm gonna do it for the people at home because
okay.
Because they like it when I draw better than Team Skeptic, because he's, Team Skeptic, he's no good at drawing. He's really terrible. So all right, so here's kind of the side view. It looks like a kind of a happy mustache, doesn't it? Of North Pole in the middle, and then somewhere in the middle, and then you've got Antarctica here and Antarctica here, right? Is that?
Yeah, but I wouldn't say it's that exaggerated on the.
I agree, it's not to scale, right? But all right, so here we are.
On the walls, it's not that exaggerated.
So here we are in North America, where now our version, our direction of down is all screwy according to the model. But if we look eye level, it's kind of downhill, right? And so we would look up. I'm going to try and draw. There you go. You'd look up and you'd still see what's there. There's something there. There's this stuff. You'd see this water or this land or whatever's there.
Okay, but what if you're looking the other way towards the North Pole?
Well, I'm not concerned about that at this
point. I know. But there is something blocking you from seeing stars looking one direction and not the other. And you say it's a globe, I say it's the Ferguson model.
No, but in every direction you look, you see the same dip of the horizon, no matter the direction. And in this one here, you would actually look up to see the horizon. People are seeing things in my drawing that I did not intend to see. But being that I'm 13 and here where it counts, I get the humor, and I did add a little unintentional, I assure you, things there. So sorry. So you would look up to see the horizon. If you're in North America, you'd have to look up, not down, and we always see it down, right? So why don't we see the Antarctic ring there? What is preventing us seeing from that, but allowing us to see the stars on the other side of it? Oh, hold on. Did your audio? I think your audio cut out. Chesh killed a stream for this. Oh, okay.
Let me see.
All right, I hear you now.
Okay. That was weird. Okay, so you know how light bends right at the horizon? The stars will actually bend downward.
Yeah, but when light bends down, it makes things appear higher, not lower.
Right. So we're looking up, right? Higher.
Yeah. So if it curved, you're defeating yourself on that one.
Let's see how I'm doing that.
I'll draw on the other side a slight curve So if there's looking worse all the time, people. If there's a slight curve, you would actually see the apparent horizon would be even higher. It would make Antarctica look even higher if it was curved. Here's the light curving down. Antarctica would appear even higher. So it doesn't help. Right?
It's curving over Antarctica wall, basically, is what I'm saying.
Yeah, but there's no reason why we wouldn't. There's still no reason why we would not see Antarctica.
Just the atmosphere itself is what I'm thinking.
But we see the stars. Right? There's no place in the sky where we look and see nothing. Right? If it's like if
that's because the light bends around the
all right, you're gonna have
gravity.
to do. All right, let me do this. That doesn't make any sense, but I know that you can probably work out on your own instead of right now on the spot.
Yeah.
Do the stuff. Actually draw some curves where the light is bending down and see what happens and see if you can make it work. And I don't think you're going to be able to.
Okay.
Okay.
Can I explain the Ferguson model if you don't mind?
Yeah, go ahead.
Okay, so I'm
I'll eat
thinking
some pizza.
how gravity works on the Ferguson model is much like if you go in your bathtub and take a shower, fill up the bathtub with water, right? And then drain the water. You'll see it through the drain hole, the water spiraling, right, curving, and pretend that drain hole is Earth. Pretend that Earth is actually a black hole, just presume it and imagine that. And what I'll do is I'll even when I sell some merch for YouTube, I'll get some drain plugs that can replace the ones in your bathtub, and I'll put some fly weights on there, and they'll float up with the water, the sun and the moon and the stars and everything. Satellites, all those satellites will float up, and then as that centrifugal force draws the water down, you'll see them start to curve around, and that's how the satellites are suspended, the moon's suspended, the sun's suspended above Earth, and pretend space-time is the water itself suspending it. Centrifugally, it's getting thrown out centrifugally, and then as, of course, the warp of space-time is pulling everything down. It wants to pull everything down, but because of that centrifugal force, it's just being forced outward and up away from Earth.
Okay.
Would that make any sense?
No, but it's fun. What when you first started posting on Facebook, I'm like, dude, you have a thing for writing, like,
yeah,
cool science fiction ideas. You could write a book, and that could be like the underlying premise of it for some sci-fi book.
Right.
But this is reality, and so we have to deal with the actual physics. This pesky stuff of we can't violate the laws of physics that we figured out. So.
Can I share my screen with you?
Yeah, all right, here I got to make sure that the default setting on here doesn't let you. So hold on, all participants. There you go. I wish in Zoom I could have it default to allowing everybody, but it doesn't let me. So there you go. It is giving you a chance.
Okay, so I would like to share my screen with you, and let's see here. Let me share this one. Share. Okay, so this is a little slide I'm working on, a PowerPoint slide. A centrist view of the debate between globe versus flat Earth, questioning the accepted paradigms on both sides of the debate, right? And it's by me. Here we go. We're gonna try to attempt to solve the yet unsolvable two-body problem and the three-body problem. And then you have non-Euclidean space-time versus Euclidean space-time, right? You see how that gravity works on a globe versus on this flat space-time?
Well, that flat space-time looks much more warped than the other.
Right. And that's
Wait,
what
wait.
I'm trying to...
Do you mean the unsolvable three-body problem? Not. Oh, wait.
There's two unsolvable problems. Right now we have Albert Einstein's two-body problem that's unsolvable, and we have the three-body problem of Newton that's unsolvable.
So Clive Wells says no, but continue.
Okay, we'll have to talk to Clyde Wells for a little bit. Okay, this is the three-body problem, right? You have the moon between the sun and the Earth. You would expect the moon to be pulled away by the sun's gravity once it reaches.
No, you would not. It's not.
Well, according to Newton's laws,
it's not stationary. It's moving, and the Earth being closer and has a larger immediate gravitational pull on it, we do not expect it to go flying away.
Okay, so let's see here. Next, this is where I'm getting this information from.
Okay.
The three-body problem of Newtonian physics, right? You could click on this link. I could share it to you if you like.
That's just a GIF. Is that all you want to share?
No, it actually explains the GIF itself.
Oh.
Oh, you know what? Let me go here. Let me copy this. Copy. And let's see how to share things. I'm going to learn
Just
something.
put it in the side chat there. And I'll send it to the groups.
All right.
So here, just so you know, Clive Wells is he knows his stuff when it comes to math. How about that? He says, we may not have an exact solution to the three-body problem, but we can solve numerically or use perturbation theory. So there you go.
Does he have a link for that? How to do that?
I don't know if he does or not. He has a PhD, and he does have a channel, and I have listened to his derivations. He derives formulas on his channel while working in the garage on stuff, and it's tough because I'm not looking at it. I'll give you that. All right, so there it is. I have this.
There we go.
I have the link. I will check it here with people and
share it with them.
Yep.
Awesome. Okay, so now let's go back to what was I sharing on my screen. This thing is getting in my way. All right, right here. Okay, next slide. Here's space-time, right? You have time.
Yeah.
Time map. You have the world line here, and this is where we are at y at the y-axis, right? In the present. And you have the past light cone. This is just a theory how the space-time would work.
It's a hypothesis.
Maybe? Yeah, a hypothesis, I guess you would say.
Okay.
But my hypothesis inverts this, where the past is actually a black hole and the future is the sun and the stars, vice versa. The past is the stars and the sun, and the future is the black hole.
Okay, if you say so.
That's just an hypothesis. Okay, so this is where I really want to get into you about what is gravity. How would it work on a flat Earth, and how it works on a globe, right? Newton says we have satellites falling around Earth, right, at an accelerating rate.
It's under acceleration.
Right.
And it balances out. Yes.
Okay. So with flat space-time, I'm saying that you're actually having satellites curve around,
Well,
parallel to Earth.
yeah. So I think what you're maybe doing is you're conflating like this conceptual three-dimensional drawing of four-dimensional space concept of space-time, and thinking that it's like actually three-dimensional and the Earth is actually at the bottom of it.
Right.
But that's not actual. That's just a way to conceptualize how space-time is bending in order to create gravity. So within
your model,
within our three-dimensional world, it's just experienced as an accelerating force between masses.
right. Okay, so on your model, the space-time is warping into the core of Earth, the center of mass, right? Where does that space-time go once it gets to the core of Earth?
It doesn't go anywhere. It's just bent.
It's just bent into like a singularity, right? A black hole singularity.
No, there's no black hole in the middle of the Earth or anything.
So where does all that bent space-time end up? At the center of mass.
It's I think you're trying to make the concept of it into a physical reality, and it's not.
Yeah, this is where I'm trying to, but as far as explaining it on a flat Earth, I'm able to say, okay, you have warp. The Earth's mass is warping downward at a rate of 9.8 meters squared a second, right?
Meters per second squared. But that's only at the surface. That's not at higher elevation. You're farther away from the center of mass, so it decreases with distance.
So now, the further away a satellite is, it's actually experiencing weightlessness, where it's not experiencing that downward acceleration.
No, it's not. No, it's not weightless. It still experiences gravity. It's less, but it still experiences it, a significant portion of it still. And it's not. It's weightless in that the balance between the pull of gravity and the centrifugal force are the same, because it's moving fast enough that they're in balance. That's why it feels weightless. But of course, gravity's still there. You're just in an equilibrium between gravity and centrifugal force.
Right. And then we'll go to the next slide. Okay, so this is what you're talking about, centrifugal force, right?
Yes.
Velocity and its direction of rotation, right? So this is what I'm thinking, how it's able to follow the curvature of space-time and not be warped down into Earth's mass, is because of the centrifugal force. Or
what centrifugal? You think the Earth is spinning? The flat Earth disk is spinning?
No, the space-time above flat Earth is spinning. The Earth is staying stationary, but everything around it is spinning.
No. I know you're trying.
Like
I appreciate your effort, but I don't think that. Zechariah,
go back to the drain hole hypothesis with the water flowing down into the drain, and your Earth is staying stationary there.
Oh my goodness. So, no. So, like I said, it seems that you're trying to make the drawings that we have done to conceptualize space-time. You're trying to make them into an actual physical reality. It's just a concept. It's not
right. But it would work on a flat Earth, is what I'm saying.
No, it would not. Because all that it is in our three-dimensional space, all that this bending of space-time is to us is just mass being attracted to mass. There's no actual curve of space-time that we can go see or be at, or there's no movement of this topography that's somehow spinning. That's not how it's that's not how it works. It's just that there's an acceleration. That's how we experience it. That's how it manifests in our three-dimensional world.
Yeah.
Right?
All right.
So but here's the deal. If I can we
Yeah, you could. I could pause this.
do you have no? Do you have more? Let's. I don't want to. Let's finish what you have, and then we'll go.
Okay. The next slide is beautiful. I love this one, and I'm going to share this link to you. Let's see here. Copy. Let me more. Oh, chat right there. You could share this. Yeah, that'll work right there. And this is a visualization of everything I'm saying with the satellites around Earth, you know.
Okay.
If you click on the link, you could actually see a GIF of it, basically.
Yeah, so it's like superimposing, looks like, the warped space-time with the, I don't know, the sun and the moon, or the sun of the Earth, maybe, or, yeah, something.
Right.
Or just satellites orbiting a mass, yeah.
Right, yeah.
Okay.
So the Earth would be at the event horizon, right?
No, hold on. There's no event horizon because there's no black hole.
Okay, well, whatever's causing the 9.8 meters squared at the surface of Earth.
Just a bunch of mass. That's all it is.
Right.
Yeah.
So there's a bunch of mass, but okay, it may not equal a black hole, you know, until it gets further down at an infinity distance between Earth and the bottom of Earth, you know. I'm thinking
I don't know, but okay, keep going.
See how down here at the cone here we have like it comes down further past the Earth? Well, that's where I visualize the black hole, but like at an infinity distance from the actual flat surface of Earth.
Okay.
That makes me.
Don't ask me if it makes sense. My answer is gonna be no.
I know.
Okay.
All right, let's go back to the last slide here, and this is on a flat Earth model. Massive satellites stay afloat in parabolic geosynchronous orbits above Earth by utilizing space-time curvature acceleration.
Now, space-time curvature acceleration could just be replaced with gravity.
But there's two forces. There's the space-time warp, and then there's the space-time curvature. So one, they have to balance each other out with equilibrium.
Whoa, this is new.
You didn't know about the space-time warp?
Hold on a second. Space-time warp is different from space-time curvature.
Yes. So the warp is going down into Earth at 9.8 meters, right? And
all right. Let me just. A word for that from Clive would be rubbish. But
okay.
Okay, keep going.
So what you're experiencing with parabolic and geosynchronous orbits is a zero-G weightlessness, which allows for the weightless floating above flat Earth. The zero weight is easily suspended by increasing atmospheric pressure gradients at the surface of Earth, which provides a buoyancy force to aid the satellites in maintaining altitude.
Okay, so one problem with that's pretty obvious is all the people that work with satellites would have to know this and deal with it somehow. Right?
Okay, so like take the ISS for example. They know that it's decaying its orbit, right? So they send up a bunch of fuel every year to keep it suspended, keep it accelerating fast enough.
Here's this your hypothesis, right? And
right.
There are ramifications of this hypothesis, and one of the biggest ones is that all of the orbital calculations that all of the dozens of different space agencies do in order to track and maintain the orbit of the different satellites that they have, none of that works if it's flat. If it's a Ferguson, if it's a dome, it's all completely different than if it's an orbit. And so somewhere, somehow, someone...
I don't see how they're different. That's a point.
Oh, there is difference. Because their location is significantly different. The amount of speed or velocity that you need in order to maintain an orbit is drastically different. None of this maps to somehow fool people into thinking that the Earth is spherical. That there isn't an analog for it, right? This would be drastically different. And so the people that are in charge of maintaining the orbits and calculating things for these satellites to stay in orbit, they would have to know about it, right? Yeah. And
I think they just know that they have to balance the forces of acceleration parallel to Earth and the acceleration trying to pull the satellites down. And so that's how they're able to maintain that orbit.
That's not how they do it. It's not that simple. Like, these people really know their stuff, right? And there's lots of people involved in knowing this and calculating it and maintaining it. And when they're going to place something in orbit, to get it to do all of the math and all the understanding necessary to do that is it's not easy. And in order to do it, they do all this work, right? They're like, well, it's going to be this elevation, it's going to be, and at this elevation, with this distance from the Earth, the spherical Earth, moving at this speed, they're going to have this particular centrifugal force and this particular gravity. And so here's where our balance is. And it all works for spherical Earth. And you're proposing a model that's not even nearly compatible and saying that somehow, just by coincidence, all the math works out the same.
To me, right? It would make sense because, like, it's just like driving a boat, or, you know.
No, it's not just like driving a boat because above a certain elevation, there's not enough air, right? So it's not about buoyancy. There's nothing there to buoyant. There's no buoyant force left because there isn't enough air to have significant buoyant force.
You know how you can accelerate a boat and it will come out of the water. It doesn't need buoyancy to come out of the water. It will just accelerate up into the air and almost take off like an airplane, you know, so with enough acceleration.
Boats don't do that.
You've never seen a boat like do that jump like a bicycle or something? I've seen it so many times.
I mean, I've taken my bike off sweet jumps. Right.
Yeah, exactly.
Have you ever taken your bike off some sweet jumps?
Oh yeah. When I was a kid, I was reckless.
But yeah, you land eventually.
Yeah.
So
you land, but if with enough acceleration, maintaining that acceleration, I don't think you'll be able to land at all.
Yeah, but you can't maintain acceleration once you leave the ground unless you have a rocket that's continually going, right? But your bike tires can spin in the air all they want. They won't give you any acceleration. So I got a couple. So hold on. Let's.
Yeah, no problem. I know I'm throwing a lot at you. Sorry.
It's 1,000 hypotheses and you haven't calculated the ramifications of them, but that's fine. Let me do this here. So B-Ball for Life sent me two pictures in email. I have them queued up. We'll look at them. How about we look at them next?
Okay, no problem.
The plot hole for $2 says, because you almost ran out of ketchup chips. Have you ever tried ketchup chips?
Nope. Is that the same as the sriracha chips?
No, they're definitely not the same. Let's see. Mr. Payne123 says, when you upload past debates on YouTube, please don't put any spoilers in the title. I like having no idea what I'm about to hear. So, all right. These are ketchup chips brought to me by Punchy. He handed them to me on March 12th, I believe. and I still have some in here.
They're stale by now. Don't eat them.
It's September 15th. They are still crispy.
Wow.
I did not like them when they were fresh. Let's see. Mandel says, we know you're replacing those chips. They couldn't still crunch like that after 8 months. I tell you the truth. These are the original chips. I am not replacing them. You cannot buy ketchup chips in that I've ever seen here. I don't know why they're still crispy. I will tell you that
on a show or something?
Oh, yeah, hold on. I will tell you the contents of this can is just water. But, all right. So, all right, hold on. I don't like eating them. I didn't like eating them when they're new. So, here's right. Here's some chips. Hold
Communion.
on. Right here. Here's a chip. Listen, I'm gonna right in front of the microphone. Do you hear that?
Yeah.
I broke it, right? I'll do another one. It actually clipped the sound. Right there. So they don't taste so good. All right. So they are the original ones. I don't so all right. So thank you, Plot Hole. Jessica G for $2 says, Multi Tom Tom, I've been halfway around the globe. Multi Tom Tom's in the chat. He's talking crap. He always does. Bella Charge. Multi Tom Tom talks crap all the time. Zechariah. He's a sort of flat earther. But he's twice agreed to come on and then backed out. What do you think about that?
I would never do that to you.
Thank you. Multi Tom Tom. Listen to Zechariah here. Okay. Let's see. Bella Charge for 2 New Zealand. Ask Team what happens when boobs get drawn. All right, I'm going to have to ask Team Skeptic what happens. Jessica G says boobies.
Oh,
Bella Charge for 5 New Zealand dollars says just here to annoy Multi Tom Tom. Now here we go. Cretan Bull for 10 Canadian dollars says the Ferguson and AE maps have the same problem. The Earth has been measured to be a globe countless times, and we have tens of thousands of pictures of the Earth, of the planet, and they all show it to be spherical. So I'll show you B-ball for life, and then I'm going to show you another picture there. And then Bella Charge for 2 New Zealand dollars says some boats do that due to aerodynamics. And yeah, there are boats that have fins underneath the water that actually cause them to lift the hull out of the water. I forget what they're called, but they're still in the water. It's the water they're resting on somehow, right? So let's see here. Oh, I didn't queue them up actually yet, but I did drop them into this folder. There we go. All right. So I'll share this with you. First, this is from B-Ball for Life. I think you should see that now, and then I'll show it to everybody. So here you go. This is a this, I don't know, B-Ball, is this, I think it seems that it's in Florida, but I'm not. Ala-Wai Boat Harbor. So there's
Ala-Wai, that sounds like Hawaii.
Yeah, it does. Maybe it is. All right. And here's a picture he took of those buildings. You see that? The bottoms are covered.
Right.
Right.
Yep.
The curve of the earth, the water is in the way. Right? And they're not, you see this little, like the well, there's a whole bunch of boats running in front of it there, but there's also in this hotel thing or whatever, the lobby that's a couple stories tall. You see that?
Yeah.
That's totally missing here. You don't see it at all. And that's
I wonder if he took a camera zoom and zoomed in, if it would come back like I've seen a lot of times.
I have never once seen zoom change the amount of hidden. Never once. So if you've ever seen that, you would be the first to have.
I could show you the video. Let me link the video to you.
where the amount of hidden changes due to zoom. This will be a first. My guess is here's my guess. The zoomed out version, it's too small to see. You don't see it at all because it's too far to see. But once you start zooming in, there's a certain amount hidden. You zoom in more, same amount hidden. Zoom in all the way, same amount hidden. That's my prediction.
You think it would be the same amount hidden the whole time?
Yep, I've never seen a variation in the amount hidden based on zoom. There is no optical phenomenon to explain that.
Let's see.
So while you're looking that up, I know what. Let's see. A pilot just sent me one that I believe he did, and I'm pretty sure of. Yep. So I will mute this.
Copy. And then let me see if I go back.
So
here we go.
All right. So you see this here? This is from Jamaica. Here's at high elevation. You can see this boat.
Mm-hmm.
Right?
Yep.
And you see how much is hidden. And he's zooming in more, same amount hidden. Zooming out, same amount hidden. Right? Even when you're zoomed out, it doesn't change how much is hidden. And now...
Oh, wait. Oh, see how it's hidden right now? You can't see nothing.
No, it's because it's too small. There's the angular resolution is too small to see it. That's not... It didn't change how much was hidden. It changed your ability to see anything. It's just too small. It merged into nothingness. That's not changing how much is hidden.
See,
so all right.
Semantics, I tell you, semantics. You guys are...
No, that's not semantics at all. That's just the angular resolution is too small that you can't make it out. So, all right. So now here we go. And I'll pause it a couple times here. Now he first of all, he went down to a lower elevation.
Okay.
Right? So if the Earth is a sphere, there must be more hidden. If the Earth is flat, there must be the same amount hidden. Okay, so here we go. Zoomed in, you see how much is hidden now. Still a good amount hidden, but there's some features that are missing that we saw at higher level. Increasing zoom does not change how much is hidden. There you go. Now he's going to...
So, like, assume you're looking at a table eye level, and then you raise your eyes up. You can see more of the table as you come up, and it's flat, perfectly flat.
But something's sitting on top of the table. You see the same amount regardless. If your eye is always above the table, if you're a small amount above the table or a large amount above the table, you always see the same amount of something sitting on the table. So now he's getting in an elevator here. And he's going to go down. But I'll jump ahead so that we don't... you can watch the whole video.
Yeah, that's fine.
So here he is, real close to the beach. Right? Now, again, if the Earth is a sphere, more of the ship must be hidden. And if it's flat, the same amount must be hidden. Now look at that. All you see is the very top of that there, the control deck.
Right,
that's all you see. And here's the cool thing. You see the waves on the edge there. So it's not like this refraction layer that's messing everything and blurring everything, because you see these distinct waves on the horizon there.
What if it's the waves coming up blocking that?
Those would be the biggest waves in history. That would be a tsunami. Because if they're, where do you think these waves are?
I would say they're like right at the surface.
Right in front of them there? Look at that wave.
Yeah.
You think that wave there, which is less than a foot tall? Now he's standing up the beach, so he's, at at least 5-6 feet, probably more than that, above the water. So a wave that is 6 feet tall could obscure the bottom 6 feet of that ship. It could.
You think so? But wouldn't that depend on elevation? Like if you're lower to the surface, you'll see less.
Yeah, absolutely. So if he's right next to the water, and his camera is less than a foot away, and a 1 foot wave comes right in front of his camera, yes, it'll obscure everything. But if there's a 1 foot wave a very far distance away, the amount that it can obstruct is very small. Like, you can block things with your thumb right in front of your eyeball, right? Mm-hmm. You move your hand away, you can't block the same stuff with your thumb. You move that thumb a mile away, now you can't block hardly anything with it, right? So waves don't do anything unless they're very close. And so he's too high to be affected by the waves. And of course, as you go out farther into the water, the waves, because you lived in Hawaii for a while.
Right.
The waves are high near the shore because the water's shallow. Out deep, they're not tall waves, right? So it's not waves, right? So
I have seen the sea levels rise and fall to expose more of the boat, just with tidal waves.
Yeah. So how tall do you think that boat is? That's a gigantic ship. That's not what we're seeing.
Yeah.
That's not it. But here's the next thing, and this is because you're not like into the conspiracy stuff, right? You're not like.
No, I know there's some curvature to the Earth, and this is what I would expect to see with some curvature. I just want to calculate the difference between a globe versus a dome.
All right, so. In 1972, there was no CGI, right? It didn't exist. So this picture here, this is a picture of the Earth taken on analog film, just wet film in a camera, nothing digital about it. It was a Hasselblad camera with real film. And then this was brought back to Earth and developed in a wet room in water with acid and whatever you use to develop. It's called wet developed, right? Or wet film to develop the actual photograph, right? And this particular archive has about 15,000 pictures. Many of them are pictures of the entire Earth. And a lot of them are just like, if you ever remember taking pictures on analog film, there's a bunch of crap pictures that are thrown in there. Why do I have pictures of my sock? I didn't need that, but you pay to develop them anyway. So that's what you got. So different pictures. There's 15,000 pictures in this archive. You can go see them yourself.
I would have to look at what kind of focal lens they were using, how pixelated the image is.
There's no pixels in an analog picture. Not
There's
like that.
No pixels?
It's not pixelated, right?
Oh, really?
And the focal length can't make something spherical or something not spherical look spherical. That's not how it does it. It's just a real picture. It's an actual, just real, regular picture taken on regular film for the day. All these pictures are that. Thousands of them. So if you're curious, if you're like, they're fake, easy. You can go there yourself, right? So this particular archive of 15,000 pictures was not put up by NASA. It was a group of people that said, hey, we want to scan those pictures and put them on Flickr. They went to NASA in Houston and took pictures and scanned them themselves. You can do it too. Anybody who wants to can go do that. So I'm going to send you, I'll do it on Facebook. I'll send you the link to go visit them yourself. These are in Houston, right? So if you ever find yourself in Houston, you can go look at these pictures yourself. So here's the thing.
Here's the thing for me is I can't make out any of the land masses. So what if I'm looking at the top of flat Earth?
Well, that's why I sent you the link I'll send you the link to the entire archive, because you can make out the land masses. Yeah, and you can make out, like, if it's a dome, you'd see all of the land masses on the dome, right? And then you'd see whatever, right? They'd all be there. But you can look at all of them and see. So I sent you the link. So we've got that. We've got pictures of the Earth taken on film. You can go see yourself. We've got measurements of the dip of the horizon that matches the radius that we. So if it's a dome of that radius. But the lands don't quite fit in. But that's fine. We've got spherical triangle or triangles with spherical excess, right? And mctoon.net/r is where that is, and I'll give you that as well. And all of those that you can do some trigonometry. I did, and I'm working on a spreadsheet to do this. When you take a triangle, and if you know the lengths and all the angles, a spherical triangle, if you know all 6 pieces of information, which we do, then you can know the radius of the surface that it's sitting on. And so I have, and it's tedious, I've typed in 30 or 40 different triangles and calculated the radius for each one of them. And they all match. About 4,000-mile radius. So you go, pictures, dip, spherical excess, and of course, people have measured the radius from Earth, from satellites in space.
I'm thinking they measured the circle of the, dome. That's
Please.
what I'm thinking.
Here's the thing. They're not dumb. They know what they're doing. That they would have to not know what they're doing in order to be confused by that,
Yeah, but so when they stack the pictures there, they take a whole bunch of pictures, right? And then they use that algorithm to merge them together with the artificial intelligence, to get the...
To what?
The super high resolution zoom that they get.
In what?
And on the satellites. The satellites taking pictures of this globe, this beautiful globe.
But the satellites that measure the radius of the Earth aren't the ones that take the pictures of the Earth. They're different ones.
Okay, so
yeah.
Those satellites are actually, if you think about it, what I'm saying is, like, they're right above the flat Earth surface. You have them going around in a radius right above Earth, just like a satellite would, just like a centrifugal force causing.
So but take the satellites don't just orbit like this. They actually go in this big wobble. It's not a wobble, actually. It's actually going one direction, but right. Because the Earth rotates underneath it, when you plot it out on the Earth, it looks like it's tracing a different arc every time it goes around. So it takes about 90 minutes to go around. So it doesn't match. It's not just going in circles, right? So try drawing out like the ISS path on flat Earth.
I have seen it.
It doesn't make any sense.
Flower.
Exactly,
it's a flower pattern.
So what's causing that to go in these different in and outs? If it's flat, it doesn't make any sense.
So if it's in an elliptical orbit around the North Pole, right? So
it's not elliptical. The flower isn't an elliptical orbit.
Or whatever, any kind of like where the center of mass it's going through a parabolic arc, right around the North Pole, or whatever the center berry point is, that it's gonna. I would say that's the North Pole. The very center is the North Pole.
Okay.
If it makes sense, I'll let me pull up this video. I'm gonna show you if I can find it.
While you're looking for that, we made pizza. My one son loves olives, but he hates pimentos. So I'm like, well, I'll take the pimentos. He picks them out. I'm like, I'll take the pimentos, and he goes and he throws them on this little corner of it. And And then he's like, hey, do you want olives on yours too? I go, yeah, sure, I'll cut them up. But he didn't hear me say cut them up. So I cut up olives, and then I threw them on my part of the pizza. He's like, oh, I already put olives on there. So I got double olives plus pimentos on my pizza. So it's very olivey.
Nice. I made pizza for my kids one time, and they wouldn't eat it.
We've done it every week since the lockdown started. The quarantine
Oh,
started.
nice.
Yeah.
Let's see.
All
Okay,
right.
I found this video. Let me go ahead and share it with you. This is the ISS path on a flat Earth versus a globe Earth.
I don't see it yet.
It's in the chat, I guess.
Oh. All right.
Oh, I didn't share the screen. I could have shared the screen. Sorry.
That's all right. I'll grab it. Yeah, see this I'm playing it now. You don't see it, but this isn't helping the flat Earth side, because there's no reason for it to do that. Why is the satellite doing that particular flower shape, where in orbit it makes perfect sense and we can actually calculate it and predict it? But what's the formula? What's the equation? What's the reason why this would happen over flat Earth?
For me, it would be because it's accelerating through time and causing that curvature, and then
No, I don't know.
That North Pole is the center of mass, basically.
But there is there is no mass point above the North Pole, because there would have to be a mass point above the North Pole somehow, right? Hovering whatever elevation the satellite is above the North Pole in order to have that there.
To me, it would just be the very center of space-time curving around.
But that's not how space-time works. It's not actually a well-shaped thing. It's just, like I said, you're trying to take the concept of space-time that people have drawn just as a way to think about it, and you're applying it to be an actual physical thing, and it's not. It's just an idea. That's all it is.
I get that.
So
it might be applicable if the Earth was flat. That would be how it would be, right?
No, but it's an interesting idea. All right. So I appreciate that. So yeah, I mean, here's the deal. In science, and let's do this. We need to kind of wrap on this.
No problem.
You get a hypothesis, and then you test the hypothesis. And a good hypothesis is a testable hypothesis. In fact, if it's not testable, it's bad and doesn't really qualify as a hypothesis if it cannot be tested. So when people describe science, they talk about the natural world. And the reason why they talk about the natural worlds is as a contrast to the unnatural world, being spiritual or psychic or metaphysical, right? So
subjective.
So you can't
subjective versus objective.
No, well, not even that. It's more of, you can't measure a ghost. You can't quantify love, right? Those kinds of things. That's not the natural world. The natural world is, here's an object. There's a satellite, and it is orbiting, or it's somewhere in space, and it's doing things, and we can point our satellite dishes at it to receive a TV signal or for a communication mechanism, right? We can do that. So if you're going to have a hypothesis about what that is, and it needs to be testable.
Joey's coming in to tell you good night. Joey's coming in to tell you good night.
What's that? Oh, okay. All right. So I appreciate that. So, yeah. I mean, here's the deal. In science, and let's do this. Let's kind of, we need to kind of wrap on this. No,
Joey's coming in to tell you good night.
Oh, okay. My daughter's coming in to say goodnight. Just a second.
Oh, okay.
You'll hear her
No
for a
problem.
second. She always wants to say hi. But I turned the camera off so nobody can see her.
No problem.
Here, hold on. Here, go. Put this in your ear.
Hi.
Hello. Hi.
Here. That's Zechariah. Say hi.
Hi.
He can't see you, so you don't need to
can't
wait.
see you.
And there's
I'm hearing you though.
there's 198 people listening to you talk right now. What do you think about that? Say hello.
Hi.
What do you think? What shape is the Earth?
Obviously round.
Obviously round. All right. Well, thank you for coming and saying goodnight to me.
I love you.
Thank you. I love you too. All right. Good night. Sleep well.
Hi. Good night.
Okay. There you go.
So, what I would say to anyone who says the Earth is round, I was like, well, a circle is round as well.
Yeah. Of course. We use in the common parlance. So.
Right.
Okay. So a hypothesis is testable. So and when you test it and find that it doesn't work, then you throw it out and bring up another one. So people have talked about, this theory of not this theory, this idea that if you were able to cheaply test hypotheses in some sort of a system, right? Like I don't know, if it was possible, then you could have a random hypothesis generator go and test millions and millions and millions of random hypotheses until you get your collection, your small collection of those that work and your big collection of those that don't, and then that would start to build a picture of reality. Of course, that's not very easy to do. So when you do a hypothesis, you want to have a good one, because it can be expensive to test a hypothesis, or at least take some effort. So make a good hypothesis and test it. And if it doesn't work, throw it out. Like the Ferguson model. I have thrown it out. It doesn't work for me. But you think that bending light could do it. So don't do this. Don't say, like, I want to make it work. Instead, say, I want to test to see if it works. And does this work? Bending light this way? No, it doesn't. Bending light this other way? Yes, it does. But does light actually bend that way in reality? No, it doesn't. Okay, that doesn't work either, right? So go through a couple of these iterations and see if any of those work. They don't. Another way to quickly disprove the Ferguson model is that distances in the southern hemisphere are drastically off. And you can see right here, I have these flight charts. And you work at an airport. You work with pilots.
Yeah,
they're
the.
they
I won't even say what I.
They don't get a choice about how to draw their flight plans. They don't get to use whatever map they want. They use a spherical map. So these are the operational navigation charts, ONC charts, that were used for decades, starting in the 50s. And these are printed on 8.5 by 11 paper, but they are actually 36 inches wide, I think, is how big they were unfolded. They're giant, right? So, and Australia's in there, and you could download them for free at the University of Texas. So you just use Google UTexas, ONC, and you can download for free every one of those charts. You can take the Australia map, and you can tape them together, and they won't lay flat because it's curved when you do it. But you can see when you do that, oh yeah, the shape of Australia is the shape of Australia. And people have used these charts for life and death reasons, because if you run out of fuel part way, you could die, right? So they've used it, and it works. So there is no flat Earth map that works. The Ferguson map does not work. This map does work. And you can check it for free. You can test it and see if it works. You can test to see if the Ferguson map works and immediately see that Australia is the wrong shape. You can test the AE map and immediately see Australia is the wrong shape, and none of the southern hemisphere flights that happen every week could happen. So there's a flight every week from Sydney to Santiago. Doesn't work on a flat Earth map.
Right. It would actually work for me, because I can understand that they're using the acceleration of space-time to travel faster, and they're using less energy.
They're using. Hold on. You're claiming that they're using. It's just gravity. The acceleration of space-time is just gravity.
Yeah,
Okay.
the curvature acceleration, right? So a straight line from point A to point B is a curve, you know, and so they're curving with the acceleration of space-time around, above the circle of Earth, basically, is what I'm thinking.
Okay, so then people drive across Australia.
Right. But that's down at the level where they're not actually being affected by the curvature of space-time. They're being affected by the warp of space-time more than the curvature.
Yeah, but the distance across Australia
Right.
is known,
Yeah.
and it's not what the map shows.
Okay. So at higher elevations, you can travel faster with more acceleration, you know? And
No.
you're not affected by atmospheric density. You're not affected by, you know, drag, more drag.
When you say this to pilots, what do they say to you?
Well, I told it to this Rob Nolan, and he's like, "I'm a pilot. You don't know nothing." And I'm like,
There are
"You're
some pilots in the chat right now. I haven't seen Rob, but somebody else is. Where'd he go? Maybe he's typed it right now. There's a couple on Facebook in the groups that are always
right.
yeah. So the size of Australia has been surveyed manually by people before satellites, and they know how wide it is, and it doesn't match the Ferguson map or the AE map. So those maps can be thrown out because they don't match reality. It's a hypothesis. It's been tested. It gets thrown out when it fails.
Cartography, right, is always shifting. The actual plate tectonics are always shifting. So when I think of flat Earth, I think of the Pangea, the original Pangea,
Right.
and then with centrifugal force.
Come on, you're out of straws, man. You're out of straws.
I'm just saying the plate tectonics can move and shift the sizes of continents all the time. So
They don't move them that much.
think you know the distances and measurements, but you'll never really know for sure.
You go tell that to people that have spent their life studying that, and they'll disagree with you, right? So you're coming from a position of not really knowing what they do and how they control for variables and all that stuff. It's definitely not that. So, but that's okay. I have another stream that I'm going to be doing in a minute here. I have a $10,000 challenge on gravity, because most flat earthers reject gravity, but they
Right.
don't have a replacement for it. Right? They just reject it and say density and buoyancy, which doesn't actually explain it at all. So I have a $10,000 challenge for them, and that's what the next stream is going to be about.
I win automatically, right? Because I gave you space-time curvature, acceleration, and warp.
No, because you don't win because you accept gravity.
Oh, darn it.
It's the other flat earthers that don't. So yeah. So, but if you want, you can watch. It'll probably be not as long as a regular one. I don't know.
No problem.
But yeah, thanks, Zechariah.
It's to get on the computer and play his Roblox.
Roblox? What,
Yeah.
dude? It's 10:00 at night. Send that kid to bed.
I know, but I took up all his computer time. So it's like, damn. Sorry. All right.
Well,
Good
yeah.
to talk to you.
Yeah, thanks
Michael.
for coming on. Thank you everybody for super chats, and thank you to my channel members and patrons for your support. It makes what I do possible. Tune in in just a minute. Oops. Tune in in just a minute. If somebody could drop the link in there quick.
Oh yeah. Just in for a minute.
Yeah, well, some of the mods can grab it. It's not Monopoly. Multi Tom is an unbeliever in this challenge. Multi Tom, you're invited to take this challenge as well. So, thanks everybody. We'll catch you in just a minute. Bye.